I welcome you all to our third lecture annotation video. Today we will start with the evolution of computers, that is the generation of computers. First, at first I would like to draw your attention to the generations and the year that belongs to that generation. During 1944 to 1958, first generations of computer were used, which was built using vacuum tubes. Then the second generation came. It is a comparatively shorter period than the first generation, and it used transistors as the building block. And then came the third generation of computers, which started its production in 1964 and went on to well over 1970. It used integrated circuit or IC, and the fourth generation computer came into being from 1971, the year of our liberation, to now. It included very large scale integration and large scale integration LSI or VLSI, and the fifth generation that we are finally using is a kind of artificial intelligence operated. So that's all about the brief summary of five generations of computer. Nowadays, when we use computers, it gives us some recommendations to what to use and what to go after, and it tracks our every movement and gives us recommendations of various sorts. So it can do that because of the artificial intelligence that is embedded in the computer system. Now let's move on to our next slides. Electronic valve. Electronic valves. Electronic valve is the was the building block of the first generation of computers. As we can see here, that it used vacuum tubes. These vacuum tubes were these electronic valves. Now here we can see a picture of a first generation of computer, and from here we can see that it is a very large machine operated by several human beings at a time. So let me mark the human beings. Here is a human being or an operator. There is an operator. Supposedly here is another operator. It took more than one operator to operate a single computer. At that time, the first of the computers, the first generations of the computer, needed to be operated by more than one operator. Now let's proceed. Here we can see the history behind the first generation of computers. The earliest attempt to construct an electronic computer using vacuum tubes appeared to have been made in late 1930s by John V. Atanasov at Iowa State University. This special purpose machine was invented for solving linear equations, but it was not ever completed. From our point of view, from our scientific perspective, what we aim to produce or what we aim to experiment sometimes ends in failure. So, but the trials, but what we learn from these trials, that what is the problem and how to solve them. So the attempt by John V. Atanasoff was the first ever known machine that tried to solve linear equations, but it was never completed. Now, now comes the ENIAC computer. ENIAC stands for Electronic Numerical Integrator and Calculator, ENIAC. It was built by John W. Mauchly and J. Presper Eckert at the University of Pennsylvania in USA. Like Babbage's difference engine, a motivation for the ENIAC was the need to construct mathematical tables automatically, this time ballistic tables for the US Army. So what is a ballistic table? You have to consult Google if you have more interest. I would not go into deep analysis of them, but for your information, ballistic tables were used in the ballistic missiles to calculate target and range of ballistic missiles, and it is a highly complicated physics calculation. So it was used for uh, purpose. Its purpose was to use for the military, and that's why it was built. And then let's move forward. The work on the ENIAC began in 1943 and was completed in 1946. Here are the characteristics of that machine. It weighed 30 tons and contained 18,000 vacuum tubes. It was also substantially faster than any previous computer. While the Harvard Mark I required about 3 seconds to perform 10-digit multiplication, the ENIAC required only 3 milliseconds. But here we can see another computer which was built, Mark I, Harvard of University Harvard. Mark I took 3 seconds to perform a 10-digit multiplication, and ENIAC, the latest at that time, latest computer at that time, record only 3 milliseconds. So if you are asked about what we can accomplish, what is the improvement from Harvard Mark I to ENIAC computer, it is this point, that it takes very less time compared to Harvard Mark I to calculate a 10-digit multiplication. Now then, the idea of storing programs and their data in the same high-speed memory, the stored program concept is attributed to the ENIAC's designers, notably the Hungarian-born mathematician John von Neumann, who was a consultant of the ENIAC project. The concept was first published in 1945 proposal by von Neumann for a new computer, the electronic discrete variable computer, In other words, advac. Now let's go through it again. The idea of storing programs and their data in the same high-speed memory. It is the fundamental block that we use now. Random access memory. The founding father or the principle used here is this. Here, it was introduced that we can store both the program and data in the same high-speed memory. And its concept was introduced by a mathematician, John von Neumann, who was a consultant of that project, ENIAC project. And he proposed in 1945 a new computer, electronic discrete variable computer, in other words, EDVAC. Now let's proceed to the main concept of the organization. Now here we can see the organization of the first generation of computer. It is somewhat similar to the analytical engine. We have three core portions. One is input-output equipment. Another is central processing unit, CPU. And the other one is main memory, which stores program and data for execution. Now, when we try to input some instructions to the computer, we use secondary memory keyboard for inputting the data. Programs, data, operator, commands, etc. are input by secondary memory or keyboard, and the data is processed in the CPU. And what instructions we need to perform, what programs need to be performed, we fetch that from the main memory, and then the instruction is given to the program control, which executes the programs, and the data, using the data from the main memory, the data is processed, and finally the output is given to the printer. This is the basic building block or working procedure of the first generation of computers. Now you have to remember that it is very important that the terminologies that we use here should remain exact as it is. You need to memorize it very well, and I know that you can do it. Now let's proceed further. In 1947, von Neumann and his colleagues begin to design a new stored electronic program, now referred to as the IAS computer, named after the Institute for Advanced Studies in Princeton. Like the ADVAC, it had general structure as in figure 1.2. General structure is like this, or basic working procedure is somewhat similar throughout the computer generations. Now in 1947, von Neumann and his colleagues began a new stored electronic computer, stored program electronic computer, now referred to as IAS computer, named after the Institute for Advanced Studies in Princeton University. Like the EDVAC, it had general structure as in figure 1.2. We have seen it in the previous slide, with a CPU for executing instruction. CPU is used for executing instruction, a memory for storing active programs, a secondary memory for backup storage, and miscellaneous input-output equipment. Unlike the EDVAC, however, the IAS machine was designed to process all bits of a binary number simultaneously or in parallel. Now here comes the improvement. What EDVAC couldn't do and IAS could was to design the process was that it was designed to process all bits of a binary number simultaneously, that is at the same time or in parallel. Several reports describing the IAS computer were published and which had far-reaching influence. It was the first of its kind to process a binary number, all bits of a binary number simultaneously or parallelly. In its overall design, the IAS is quite modern and it can be regarded as a prototype of most subsequent general-purpose computers. This is another breakthrough that we still use today, because if we couldn't parallelly process or simultaneously process all the binary bits, the calculations or communications that we do today using our computers would never have been possible. Because of its pervasive influence, we will examine the IAS computer more detail later on. Yes, we will do so. So let's move on. In 1947, Mockle formed Eckert-Mockle Corporation to manufacture computers commercially. I have told you before, everything that have a commercial production has a tremendous growth for evolution. So it is just beginning for the case of computers. The first successful product was automatic Universal Automatic Computer (UNIVAC), delivered in 1951. Just after 4 years, they came up with another upgraded version, Universal Automatic Computer, which was the first commercial computer ever produced. IBM, which had earlier constructed the Harvard Mark I, introduced its first electronic stored program computer, the 701, in 1953. Besides their use of vacuum tubes in the CPU, first-generation computers experimented with various technologies for main and secondary memory. The whirlwind produced ferrite core memory, in which a bit of information was stored in magnetic form or a tiny ring of magnetic material. And it was another breakthrough that we will come to see. Ferrite cores remained the principal technology for main memories until the 1970s. So we know that the fourth generation of computers started its journey during 1971. So up till that moment, ferrite cores memory were at that time the latest in the memory portion of a computer, memory technology for computer. Now, the earliest computer had their instructions written in binary code, which was known as the machine language that could be executed directly. We are somewhat familiar with this machine language. An instruction in machine language meaning the add the contents of two memory locations is kind of a binary string like this. This whole sequence of binary bits is used to execute this command. Add the contents of two memory locations, and this is the machine language instruction of that simple English instruction. Now again, machine language programs are extremely difficult for humans to write and so are very error prone. You have already gone through or completed your data communication course, and we know if we change a bit, any bit, then the instruction or the message changes. And that is why it was very error prone. And then we produced the next improvement. A substantial improvement is obtained by allowing operations and operand addresses to be expressed in an easily understood symbolic form such as add from variable 1 and variable 2 x1 and x2, which we referred to as assembly language as computer programs were growing in size and complexity. At first, we were only calculating addition, subtraction, then came the multiplication and division, and then we could calculate the ballistic tables. And now we are trying more operations every day. And for that, we had to use this kind of assembly language instructions. So we can communicate somewhat error free with the machine. Now the assembly language requires a special system program, an assembler, to translate it into machine language before it can be executed. This process, these three lines, would be discussed in your 331 CSE compiler design, and you will see firsthand how this takes place. So I am not going to discuss in details what is the input here and what is the output. We are just trying to figure out about the working procedures and improvements of the first generations of computer. Now the first generation computers were supplied with almost no system software. Nowadays, when we buy any device, mobile, laptop, personal computer, desktop, etc., it comes with a operating system, Windows, Linux, or Mac OS. These were the most popular in the world. But at the time of the first generation of computers, it was kind of unthinkable. It was kind of a dream, and often little more than an assembler was available to the user. It was only the assembler which was built in to the system, and at that time, because there was no Facebook, it was used for only for education or calculation purposes only. So we can imagine what they had suffered through those who use that first generation of computers. Now let's move on further. The IAS computer. As we had discussed earlier, that we will discuss in details in later. It is instructive to examine the design of the Princeton IAS computer. Because of the size and the high cost of the CPU's electronic hardware, the designers made every effort to keep the CPU and therefore its instruction set small and simple. Cost also heavily influenced the design of the memory subsystem. Because fast memories were expensive, the size of the main memory, initially 1 kilobyte, 1 kilo words, but expandable to 4 kilo words, was less than most users would have wished. Consequently, a larger 16 kilowords but cheaper secondary memory based on an electromechanical magnetic drum technology was provided for bulk storage. Essentially similar cost performance considerations remain central to computer design today, despite vast changes over the years in the available technologies and their actual costs. Now here we see what influenced the IAS computer's design and the working procedures. Cost is the number one criteria that every computer looks upon, and it should be minimized. At that time, this 1 kilo words of memory is kind of the most that they could afford, and now we use gigabyte or terabyte of memories, and you should calculate how many times we are using we have improved in the memory department from this third generation of computers. Now these are the kind of memorizing topics, so I will advance to the next slide. Now the basic unit of information in the IAS computer is a 40-bit word, which is the standard packet of information stored in a memory location or transferred in one step between CPU and the main memory M. Each location in M can be used to store either a single 40-bit number or else a pair of 20-bit instructions. The IS number format is fixed point, meaning that it contains an implicit understood binary point in some fixed position. Now here we see the important bits of the IAS computer. The IAS instruction consists of 8-bit operation code by opcode, which follows by a 12-bit of address A that identifies 1 up to 2 to the power 12 or 4K 40-bit words stored in M. M is the main memory. The IAS computer thus has one address instructions format which we represent symbolically, operation, and the address represented by A, which is a 12-bit address, 12-bit, and the operation, the opcode, it is 8-bit. Previously, we have known we can use M, which stores a 40-bit number and a pair of 20-bit instructions. So what we have seen here, the instruction is 20-bit, 8-bit plus 12-bit, and this 12-bit identifies a 40-bit word which is stored in the main memory. Now the IAS have two key aspects, which are a small set of high-speed storage called registers, which serve as implicit storage location for operand and results. Operands are the things that we used on the by with operators. A program's instructions are stored in M, the main memory, in approximately the sequence in which they are executed. To recap these 2 points, the IAS first introduced the concept of registers, which is a small set of high-speed storage devices which serve as implicit storage locations for operands and results. Operands are the things that we use the operations, and results are the results of that operation after we execute the instruction. And programs instruction are stored in the memory locations sequentially. That is, for example, we want to execute this sequence. So at first we need to do this addition, and then with the result this subtraction. So this program instruction should look like this. First we stored the addition, and then we stored the subtraction. The sequence one should add the two numbers, and the next instruction should subtract the two numbers, the result from the addition, and another number to subtract from the result of the addition. Now then let's move forward. This is the figure of the organization of the CPU and the main memory of the IAS computer. Here we see this is the main memory, which stored about around 4K words. This should be 4096, 4096, and this should be 5, and this should be 4, and this is 5. 4K words that we can store in the main memory. And here is the program control unit, or the PCU. Here is the memory address register. IR is the instruction opcode register. IBR, next instruction buffer register. And PC, the program counter. And the most important part here is the instruction decoder. And now we will see the arithmetic logic unit, which performs the actual process of the operation. Data processing unit in here. There is the general purpose data register, which stores the data which we fetch from the main memory. AC is the accumulator register, where the actual calculation occurs. MQ is the multiplier quotient register, which stores our various results. Now I will give you a minute to go through this slide, and then I will move forward. I think it would be better off if we start from here in our next class. We will discuss from this structure, and please go through the next couple of slides so you can keep up. I will correct your slide and your understanding in the next class. Thank you all.